Hello and welcome to the channel Science, Maths and Engineering. Today we are going to solve the first part of a mechanical engineering paper, the examination for which was conducted by the Directorate of Technical Education Assam for the post of Assistant Professor in 2020. Now, all questions in this paper were from previous year GATE question papers and a pie chart is shown to give an idea of the number of questions from each year. So, let's get started. If sigma 1 and sigma 2 are algebraically largest and smallest principal stresses respectively, the value of the maximum shear stress is, the answer is, it is tau max is equal to sigma 1 minus sigma 2 by 2. So see, OZ is sigma 2 and OF is sigma 1 in this Morse circle, and here sigma 1 minus sigma 2 by 2 means the radius of this Morse circle EZ, or which is also equal to EH, and that is the maximum shear stress. Okay, next question. Consider one-dimensional steady-state heat conduction along x-axis through a plane wall with the boundary surfaces x equal to 0 and x equal to L maintained at temperatures 0 degree centigrade and 100 degree centigrade. Heat is generated uniformly through the wall. Choose the correct statement. A. The direction of heat transfer will be from surface at 100 degree centigrade to the surface at 0 degree centigrade. B. The temperature distribution is linear within the wall. C. The maximum temperature inside the wall must be greater than 100 degree centigrade. Or D. The temperature distribution is symmetric about the midplane of the wall. So this is a very interesting question. So let's solve it. See, the 1D heat conduction equation is d2t by dx square plus q dot by k is equal to 0. So from here, when we integrate, we get t is equal to minus q dot by k into x square by 2 plus c1x plus c2. Now once we put our boundary conditions, we get t is equal to minus q dot by k into x square by 2 plus 100x by L plus q dot by k into Lx by 2. Now, even if we put T is equal to 273 Kelvin and here T is equal to 373 Kelvin, then also the same equation we are going to arrive at. Now, you see, for maximum temperature, dt by dx would be equal to 0. So, dt by dx we already have. So, from here, when we see that our x becomes 100 by L into k by q dot plus L by 2. So, that means what? Maximum temperature occurs at a distance where x is greater than L by 2, as we see k, q dot and L are all positive numbers. So, let us take that the maximum temperature occurs at maybe 0.9 L. We just want to see whether T max becomes more than 100 degree or not. So, if we put x equal to 0.9 L, so from here we get T max is equal to this equation, and when we simplify it, we see that T max becomes 101.25 degrees centigrade. So, as this temperature inside the wall is greater than 100 degrees centigrade, so the heat transfer is then not from the surface of 100 degrees centigrade to the surface at 0 degrees centigrade. Again, the temperature distribution is not linear because the temperature has to first increase from 0 to this 101.25 degrees centigrade and then decrease to 100 degrees centigrade, right? So this is again not asymmetric, this is asymmetric. As we see at 0.9 only it became 101.25, so it is not symmetric. So what we can conclude is that the maximum temperature inside the wall is indeed greater than 100 degrees centigrade at some point. Another thing is that this is asymmetric. We can also see from our previous equation where we get x is equal to 100 by L into k by q dot plus L by 2. So we know that the maximum temperature always occurs at a point more than L by 2 and not at L by 2. So it is not symmetric. So next question. In a machining operation, if the generatrix and the directrix both are straight lines, the surface obtained is, so it is a plane. So for different other combinations, it is given here. You can have a look. Next, in solid state welding, the contamination layers between the surfaces to be welded are removed by, so these contamination layers are removed by plastic deformation. So next, water specific heat is given at 80 degrees centigrade. So TH1 is 80 degrees centigrade, enters a counterflow heat exchanger with a mass flow rate of 0.5 kg per second. So hot water, so its uh, mass flow rate is 0.5. Now air Cp is given, enters at 30 degrees centigrade. So Tc1 is 30 degrees centigrade with a mass flow rate is again given, and the effectiveness is given as 0.8. So the log mean temperature difference is to be found. So let us solve. See, TH1 is given, TC1 is given, M dot H is given, M dot C is given, C of C is given, and C of H is given. So effectiveness is Q actual by Q max. Now Q max would be what? Whichever fluid has lower specific heat multiplied by the mass, so that is M dot C. Now if we again multiply that by the maximum temperature difference possible, so that is would be Q max. No, maximum temperature difference what? When the cold fluid, if the cold fluid has lower specific heat, if the cold fluid attains the temperature of the hot fluid in at inlet, so that is the maximum temperature difference. Or if the hot fluid becomes so cold that it attains the temperature of the inlet of the cold fluid, then it's the maximum. However, how from where it is derived, from what is the driving force, it is like how much is the specific heat, because if the specific heat is more, then it will take more heat, so it won't be able to go to that temperature. So from here we get Q max is M dot C into Cc into Th1 minus Tc1, because once the air here in this case air reaches this maximum temperature, so suppose air gets to the temperature of 80 degrees centigrade, it can no longer cool this hot fluid, right? So that is the maximum heat transfer would be for the air here in this case. Now effectiveness is Q actual by Q max. Now Q actual is how much? M dot C into Cc into Tc2 minus Tc1, and then Q max is M dot C by into Cc into Th1 minus Tc1. So from here we get Tc2 is 70 degrees centigrade. Now again actual heat transfer is M dot H into Ch into Th1 minus Th2, which is also equal to M dot C into Cc into Tc2 minus Tc1. Now from here we can find that Th2 is 40 degrees centigrade. So our delta Ti, that is the temperature difference at inlet, as is a counterflow heat exchanger, would be Th1 minus Tc2, that is 10 degrees centigrade, and delta Te, that is temperature exit difference, is Th2 minus Tc1, which is again 10 degrees centigrade. So our log mean temperature difference is 10 degrees centigrade. So next, in the engineering stress strain curve for mild steel, the ultimate tensile strength refers to, so it refers to the maximum stress. Next, now the surface integral equation is given and is to be evaluated over a sphere, okay, and the velocity vector field is given as f equal to xi plus yj plus zk, right? And then we have the equation for the sphere is that x square plus y square plus z square equal to 1. Okay, now we need to find out the value of this surface integral, right? So the answer is the equation of the sphere we know. So that means what? Radius of the sphere is, so this one r x square plus y square plus z square is equal to r square is the equation then. So r is 1 from here. Now we have this from Gauss divergence theorem. The double integration of the surface into f dot n into dA is equal to the triple integration of the volume into divergence of f into dv. Now if we put our equation from here, we get that our divergence dot f, that is equal to 3 here. So our answer is 3 by 4 into the integration of the volume. Now integration of volume dv, so it becomes v. Now v is what? 4 by 3 pi r cube. So we have only pi r cube. Now r is already 1, so answer is pi. So the surface integral, once we calculate the integration, it is pi. So next, the figure shows an idealized plane truss. If a horizontal force of 300 Newton here is applied at point A, the magnitude of the force produced in the member CD is. So let's see the answer. See, if three members meet at an unloaded joint, unloaded is the important point here, unloaded joint, and then if two of them are collinear, the third member is a zero force member. So if we see at point B, AB and BD are collinear and BC meets at B. So what we have is that BC is a zero force member. Now again at this point C, AC and CE are collinear members and BC is a zero force member now. So CD would also be a zero force member. So F of CD is 0 Newton. So next, the total emissive power of a surface is 500 watt per meter square at a temperature T1 and 1200 watt per meter square at a temperature T2, where the temperature is in Kelvin. Assuming the emissivity of the surface to be constant, the ratio of temperatures T1 by T2 is, so the answer is, from Stephen Boltzmann's law we get E is equal to epsilon into sigma T to the power 4, where epsilon is the emissivity of the body, sigma is the Stephen Boltzmann constant, which is 5.67 into 10 to the power minus 8 watt per meter square per Kelvin to the power 4, and T is in absolute temperature, that is in Kelvin. So E is the emissive power of the body. So E1 would be equal to epsilon 1 into sigma T1 to the 4, and which is equal to 500. Then E2 is epsilon 2 into sigma to the T to the power into sigma into T2 to the power 4, which is equal to 1200. Now we have given that epsilon 1 is equal to epsilon 2, so we get E1 by E2 is T1 by T2 to the power 4. So from here we get T1 by T2 is equal to 0.803. So next, a CNC vertical milling machine has to cut a straight slot of 10 millimeter width and 2 millimeter depth by a cutter of 10 millimeter diameter between the points 0, 0 and 100, 100 on the XY plane. Now these dimensions are in millimeter. The feed rate used for milling is 50 millimeter per minute. So the milling time for the slot is, so the answer is, see, now the width of the cut and the diameter of the cutter are of same. So the cutter can just cut the slot in one pass. Next, total length of the slot would be how much? So one point is at 0, 0, other point is at 100, 100. So our length would be root over 100 square plus 100 square. So it is 100 root 2. Now feed rate F is 50 millimeter per minute. So therefore our time would be how much? The length divided by the feed rate. So what we get, 100 root 2 by 50, that is in minute. So we get 2 root 2 minute, or it is 169.705 seconds, which is approximately equal to 170 seconds. So next, at x equal to 0, the function fx is equal to mod of x has, the answer is, it is a minimum. So see, a point where the function has its lowest value is a minimum, and a point where the function has its highest value is a maximum, that we all know. Now what is the point of inflection? It is a point where the function changes its sign. Now here the function does not change its sign. So here it is a point of minimum, and here this I have also shown in this graph. Right, next question. The ratio of momentum diffusivity nu to thermal diffusivity alpha is called, so it is called Prandtl number. So the definition for the Nusselt number, Biot number, and Lewis number are also given here. Next, A force of 400 Newton is applied to the brake drum of 0.5 meter diameter in a band brake system as shown in the figure, where the wrapping angle is 180 degree. If the coefficient of friction between the drum and the band is 0.25, the braking torque applied in Newton meter is, the answer is, see, we know T1 by T2 is equal to E to the power nu theta. Okay, so nu is already given as 0.25 and theta is 180 degree, that is pi. So our T2 becomes T1 by E to the power mu theta, which is equal to 182.375 Newton. Now braking torque would be equal to T1 minus T2 into R. So which is equal to 54.406 Newton meter. So next, a solid circular shaft needs to be designed to transmit a torque of 50 Newton meter. If the allowable shear stress of the material is 140 megapascal, assuming a factor of safety of 2, the minimum allowable design diameter in millimeter is, so the answer is, see, T we know is 50 Newton meter, tau allowable is 140 megapascal, factor of safety is 2. So tau max would be tau allowable divided by factor of safety, which is 70 megapascal. Okay. Now polar moment of inertia J is equal to pi by 32 d to the power 4. Now we know that T by J is equal to tau by R. So from here we get that minimum of D is equal to 15.379 millimeter, or D min is 16 millimeter. So the diameter of the shaft has to be a minimum of 16 millimeter. So next question. The thermodynamic cycle shown below, there is this TS diagram, indicates. So what does it indicate? See, if we come here, from 1 to 2 it is going, so compression, then 2 to 3, that is heat rejection, 3 to 4, that is expansion, and 4 to 1, that is heat addition. So this is exactly the reverse Breton cycle. So next question. A circular solid disc of uniform thickness 20 millimeter, radius 200 millimeter, and mass 20 kg is used as a flywheel. If it rotates at 600 rpm, the kinetic energy of the flywheel in joules is, so the answer is, see, we know radius, we know mass, we know, so moment of inertia is how much? I is equal to mr square by 2, so it will be 0.4. Now angular velocity omega, we know 2 pi n by 60, so it is 20 pi per second. So kinetic energy of the disk is half of I omega square, so which is equal to 790 joule. The next question. 3 cards are drawn from a pack of 52 cards. The probability that they are a king, a queen, and a jack is, so the answer is, see, number of exhaustive cases is 52C3. That means 3 cards can be taken out of a pack of 52 cards in 52C3 different ways. So this is equal to 22 to 100. So number of ways one king can be taken out of these 4 kings that are there in the pack is 4C1. Similarly, for queen is 4C1, again jack is 4C1. So the number of favorable cases would be multiplying this all 3 parts. So 4C1 into 4C1 to 4C1, so it is 64. So therefore the probability of a king, a queen, or a jack is 64 by 22100, or 16 by 5525. So next, the spring constant of a helical compression spring does not depend on, so the answer is, the spring constant for a helical compression spring is given by K is equal to capital Z small d to the power 4 divided by 8 d cube n. Now K is spring constant, G is modulus of rigidity, and small d is the diameter of this wire, and capital D is the mean diameter of the coil, and N is the number of active coils. So it does depend on the coil diameter, it does depend on the number of active turns, and it does depend on the wire diameter. However, it directly does not depend on the material strength. Z also shows material strength in twisting, but we here, if we see the material strength, that means any Young's modulus or the other parameters is does not depend on, and here twisting is not an effective way of representing the material strength. So materials is, so the compression spring constant does not depend on the material strength is the correct answer. So next, a circular rod of length L and area of cross section A has a modulus of elasticity E and coefficient of thermal expansion alpha. One end of the rod is fixed and the other end is free. If the temperature of the rod is increased by delta T, then so what happens? You will see. See now, one end is free to expand, right? So with delta T, the thermal strain that is developed, it will elongate, but no stresses are developed as it is free to expand. Right. So change in length is delta L is L into alpha delta T. So strain would be delta L by the L. So it is alpha into delta T. So next question. A cylindrical tank with closed ends is filled with compressed air at a pressure of 500 kilopascal. The inner radius of the tank is 2 meter and it has wall thickness of 10 millimeter. The magnitude of maximum in-plane shear stress is, so the answer is, see, here T by D is equal to 1 by 400. So as this is less than 1 by 10, so it is a thin cylinder. Now maximum in-plane stress would be tau max is equal to PD by 8T. So from here we get the maximum stress is 25 megapascal. So with this we come to an end to the first part of this question paper. So come with the subsequent parts very soon. So stay tuned and thank you for watching.